All right, confirmatory factor analysis. It's based on theory. So you need at least 3 items for it to be stable. And the goal is to create a model off of a theory. So it's basically what you were doing today.
Why am I not seeing confirmatory factor analysis?
It's assumed under the FA of factor analysis.
Oh.
So it's 2 types.
You're starting down there?
Yeah.
Okay. Sorry.
So can you repeat that?
Yeah.
No, we're starting at the top. Factor analysis, there are 2 types. There's confirmatory and exploratory. Confirmatory is what you were doing today. Exploratory is what you were doing last week.
Could you repeat what it means?
Yeah, it's based on a theory. So we have an idea of constructs and we want to see if it matches reality.
That's confirmatory, right?
Yep. So the statistic used obviously is the chi-squared, and we want it to be low or not significant. And so it's a test between the real data, the measured data, and the factors researchers have identified in the model or the latent variables.
It depends, the test between the real data
And the factors researchers identify in the model or the latent variables. So when you got done running your confirmatory factor analysis today, you pulled up the data view with the model fit summary data and had the chi-square and the Rmsea, CFI, GFI, NFI, you know all of those? Okay. You want to review those, so you do, and then you want to know the parameters for each of those for the exam, because I guarantee it's going to be on there. It was, and it tripped up a lot of people last semester because we didn't study it well enough.
Can you go through those?
Yeah. So Rmsea, it measures residuals. The lower the better, but ideally you want less than 0.08. So basically anything between 0.08 and 0.1 means that it's then a moderate fit, and anything greater than 0.1 means your model's a poor fit.
Can you say the numbers again?
Yeah, anything lower than 0.08 is a good fit.
Anything below 0.08 means it's or above 1 is a good fit?
No, anything lower than 0.08 is a good fit.
between 0.08 and 1 is moderate, and if it's
0.1.
0.1.
Yeah, 0.1.
Oh.
Let me,
And which one is bad? If it is over 0.1.
0.1, greater than 0.1 is a poor fit.
all right. There, yeah. So on the page, doesn't give page numbers, but in the output that or the printout that he gave you today, the definitions of them are the guide, the numerical guides of what you're looking at are written on there. So we'll go through it again. So for CFI, we want something greater than 0.95. And that's the same actually for the GFI and the NFI. So the larger the better. So greater than or equal to 0.95 is an indication that your model is a good fit.
What were the other ones? The CFI and the other ones?
GFI and NFI.
So it's greater than 0.95, it's good?
Yep. And then for your chi-square, yeah, we don't want it to be significant.
For these,
Yeah,
For chi-square.
just for chi-square.
It'll be like
So
more than
it's
0.05.
indicated on the top of the model fit summary, if you look at that page, the CMIN, default model, and then he has it indicated significant, and then he has the little chi-squared indicator. It's not a good thing. So we don't want it to be significant. Okay?
But he's also said though, with a big sample, it's okay if it's significant.
Right. These are just guidelines. So all of, other factors go into it. So like you said, big sample size, you're more likely to get significant, so it's less of an issue. Right.
Do you know what type of error is associated with a big sample size? Type 2. So you just have to be careful of that.
How do you know that's so easy?
I have to think about it.
50% chance for mistakes. No, but really, like, conceptually, how do you know you risk type 2?
Because larger samples just inherently are likely to produce statistically significant results.
Due to chance.
Yeah. Just because there happens to be naturally more variability in really large sample sets. So it's kind of like Goldilocks is the way you want to think about it. You don't just want a big, big sample, and you don't just want a small sample. You want the one that's kind of just right.
It's a good analogy.
Yeah, I said it. But just a reminder, you need at least 3 items to be stable, for the model to be stable.
What happens if it's not?
Then you would have something like, she said it in class today. What was the name you gave it?
Is that the just identified?
Yes, exactly. Thank you. Yeah, it's just identified. So you don't want it to be under-identified and you want it to be over-identified.
we need at least 3 variables.
You need at least 3 items. It's not necessarily variables because we're talking about latent variables at this point, so they're unobserved. So observed variables, and you'll need to know differences between squares, circles, and ovals, right? So squares are your measured variables. You've given somebody the BDI, that's your depression score that you're going to put in your model, right? You've given somebody the PCLC, that's your PTSD score. Now let's say you've given these 2 items and you've got a structural equation that you're doing where you want to look at partners' distress or individuals' distress and how it affects relationship satisfaction, right? You've got 2 measures that could potentially fall under the realm of individual distress, their PTSD score and their depression score. So you can say, I'm going to take these 2 measures and see, does this fit the latent variable distress, right? So it's taking these measures or taking these observable things and saying, how are we, do they fall under one branch? Can we call this one type of thing like we did with, I think you identified it as type A personality at first in your model, right? It's all of those observed things are creating this personality type. So the ovals are the latent variables, those are the unobserved. That's the one you're creating, that's based on theory. All right.
So how did we get from CFI to that? I'm confused. Because we were just
what?
line over CFI, GFI, NFI.
Oh, those were model fit indices, or those were your model fit, and your whole model itself is what you were doing in confirmatory factor analysis. Yes.
You said there were squares, ovals, and circles?
Yes.
So the square is a measured variable, the oval is a latent variable, what's the circle?
Circles are errors.
Thank you.
And I think he does a good on your diagram rules. You'll want to know all of those.
Which,
First page of your SEM
for today.
for today, your PowerPoint.
Do you remember when we did these? Oh, what examples?
Yeah. We'll go once we get into,
Both of them.
yeah, so go into exploratory.
All right, so the exploratory factor analysis, this type of statistics, you're not testing your model. Okay, so there isn't a hypothesis. Okay, you're just wanting to see what clusters together. Okay, and your goal is to create a new factor or a new latent variable.
And this is what you did last week, right? You ran the model, you see which item it loaded, how many factors decided to keep, and then you see which ones, what were the markers that loaded on factor one, and then you named the factor based on those loadings.
So it helps you figure out like what your constructs are going to be.
Right.
Okay, so you can do principal component analysis.
Oh, hold on. On exploratory factor analysis, you need at least 200 subjects or 10 subjects per item.
Say that one again.
Yeah, but it might be up again.
You need 200 subjects, which is a lot. Or like we used for the last test, 10 subjects per item.
And so for exploratory factor analysis, you have two types. You have principal component analysis and factor analysis. So both of those are two types of exploratory factor analysis.
Factor analysis?
Yes. So yeah, factor analysis or exploratory factor analysis is broke up into two types. Principal component analysis and factor analysis.
Okay, so for principal component analysis, the way we talked about it last year was that you're smashing items into a few components. Okay, and it looks at the total variance. What else do you have for this one?
I have that the variables create factors or components. And it stresses differences rather than similarities. And because it's dealing with total variance, it's obviously, it's going to account for more variance than factor analysis. And when we get into talking about factor analysis, you'll see why.
That counts more because
It looks at total variance.
In fact, this is shared.
And so in factor analysis, it's looking at the shared variance. And the goal is to try and find the similarities among variables. So it's more related to theory than principal component analysis.
Okay. That's like John. Yeah.
But not as,
It's one related to theory.
Yeah, it's more related to theory than principal component analysis, but not as much as confirmatory factor analysis.
As confirmatory factor analysis?
Ready to one? So factorability, it's looking at whether or not there's enough correlation between items to perform a factor analysis in the first place. It looks at whether or not there's enough correlation between items to perform a factor analysis.
What is this for?
Factorability. So statistics of adequacy, there it goes under factorability. It's the KMO. These are each out. It needs to be above 0.7. It looks at how strong the correlation is. So this is not a concept written out. It goes under factorability.
What
So
is
this
it
is
called?
KMO.
KMO, Kaiser, Meyer, Olkin.
And it makes sense that it should be greater than 0.7 because you're wanting things to cluster together.
Statistics of adequacy, KMO, Kaiser, Meyer, Olkin, and then what about them?
Needs to be above 0.7.
Looks at what?
How strongly the factors
Correlate.
are correlated.
There's also the Bartlett test, and we want it to be significant. Robbie, what does that look on your face mean?
Okay, so the difference between the two is that for Bartlett's, you're trying to see if there are any correlations in general, and the KMO, you're looking at how strong the correlations are.
They're both factorability tests.
Yes. So, to go back to something a little bit more basic, what is a factor? Don't think statistics necessarily, just,
Very
Construct.
yeah, so when we're talking about factors, these are clusters of items that are highly correlated. So we try and move away from saying variable here. Okay, so again, a factor is a cluster of items which are highly correlated. Okay, you can also think of it as like a latent variable that you're creating.
So now we're on rotations.
We can do tribute item.
No, I think we can do rotation. So rotation overall is adjusting the model to account for as many factors. And so conceptually think about it is it's trying to get the best fit for the model by wiggling it around to kind of capture more of the data. It also maximizes the loading of each variable on one of the extracted factors while minimizing loading on other factors. Yes, of course. It maximizes the loading of each variable on one of the extracted factors while minimizing loading on all other factors. It maximizes the loading of each variable on one of the extracted factors while minimizing loading on all other factors.
Were the extracted factors like the elements, or the factors that made up like type A, as opposed to everything else would have been not an extracted factor?
Right, or like, yeah, you would be defining which one you're wanting to place emphasis on, which one you're trying to get to fit, and then it'll hold the other ones. You'll minimize the other ones. So there are two types of rotation. There's orthogonal and there's oblique. In orthogonal rotation, factors and variables stay independent of one another.
Factors in what?
Factors and variables stay independent of one another. And each rotation is only done at 90-degree angles. It's based on theory and is somewhat suggestive. Well, subjective, not suggestive. Difference.
It's a little theoretical, just a little. Do you know which test you use for this one?
Varimax, yeah.
Varimax.
What's the name of it?
Varimax. Varimax. This one's not showing.
Uh-huh.
And this gives you your reproduced correlations, so you can see how far off you were. So what you'd hope to find is to get small residuals, meaning that you've only made you only have a little bit of error. Sure. So you're looking at the reproduced correlations, and you're seeing how far off you were. Okay, so you're hoping that they're small. You want small residuals, and remember residuals are errors. So if you have small residuals, meaning you probably did a good job.
What's considered small?
0 to 0.1 means you did a good job. Smiley face.
0 to
0.1. Okay, and to do the orthogonal rotation, the factors need to be correlated less than 0.3. Okay, so oblique. These factors are not completely independent. The factors are not completely independent. Okay, so there is some correlation. Okay, and it uses acute angles. Before we said the orthogonal used 90-degree angles, now we're talking about acute angles, which is why when you think about this, you can think of it like an X for the oblique, and then the orthogonal is more like a cross. And this uses, was it the Oblamin?
What?
Oblamin, O-B-L-A-M-I-N. Okay, and this is when your factors are correlated greater than 0.3. This is when you would use the oblique rotation. Because again, with oblique, things correlate. Factors are correlated. That's just reality.
0.03 or 0.3?
0.3.
Because with the oblique, they're what? Correlated?
Yeah, because with oblique, you're talking about how things are correlated and That's why you use this when factors are correlated greater than 0.3. Should we say this is a correlation matrix?
Yeah, we did, I think. Oh,
So in the output, when you're trying to find these, the orthogonal, you're looking at the correlation matrix. And yeah. Have you guys heard that before? Which matrix to look at for which type of rotation?
No.
You have structure matrix.
yeah, I just have it in the reverse. So for orthogonal data, I have that you look in the rotated component matrix. Maybe it's both.
Where?
I have that you look in the rotated component matrix for orthogonal, and that you would look in the factor correlation matrix for oblique.
Question.
Yes.
So in the orthogonal one, you're hoping to get small residuals when you do the Rmsea test.
Yeah.
So small residuals, and that's the error. Are you at all like looking at a difference between like the correlation matrix and the rotated component matrix, or is it just that those correlations have to be small? You know what I'm saying?
Say the last part again. What was the road?
So you're trying to get small residuals. Does that rotated component matrix give you those residual values, or do you have to use that value and find the difference from your original correlation matrix?
I have that you have to find, because it's going to give you the correlations, and that you have to find the difference from the original.
So then you would probably have to look at both of the matrices.
I think the rotated component matrix is after you've done the Rmsea test, which is essentially what you were saying.
Okay.
No, rotation is just trying to get your model to fit.
Right.
So these are two types of ways of adjusting your model to make it capture the best. So it's like saying, so here's our predicted model, we're going to adjust it slightly, and then depending on how you've adjusted it, then you take whatever the adjustment was made to the original. So it's choice of adjustment. So it's not differences between one adjustment and the other type,
Okay.
right?
And if that difference is less than 0.3, that's good? That-
If the difference is less than point, what was the model fit indice that you had? That you said it was like 0.1 or? you're doing
0 to 0.1.
0 to 0.1, it's a indication that your model is a good fit.
But is it in the difference, or is it just that residual value that you get from the rotated matrix? That's my question.
Your
So this
rotated
is-
matrix isn't going to give you residual values. It's going to give you correlations.
Okay. So then when we said that we're hoping to get small residuals between 0 and 0.1,
You're looking at the correlation, so depending on what type of rotation you decided to use, and then looking at the original correlations. Remember when he was talking about with the reproduced correlations, it's the same concepts. So when you're doing your structural equation modeling, you're adding your paths together and then looking at, well, what is the overall correlation between this, you know, A and then B, and then you want those two to be equal, right?
yeah,
It's the same concept.
okay.
So you don't want them to be different from each other?
Correct.
And so before the models, before you've kind of rotated it to try and capture as many of the factors that might be contributing to more of the variance, is that seen as the eigenvalues of the row squared down? Is that the value that's in there? And then after you've rotated it, you tended to see the one that was like the largest contributor maybe come down a little bit, and the others kind of flatten out and rose a little bit.
Right, when you look at your rotated matrix, though, it's going to only show you the ones that, the
Extracted.
factors that you've already extracted. It's not going to do it for all of the potential factors that you didn't
So-
keep. But
So
yeah,
you
it's-
visually see it, but then you rotate it and then you see the.
exactly.
flat
It's
out,
trying to minimize.
Sharing
So
it a little better.
just like your linear regression, the line of best fit, where you're trying to minimize the line that you've put through your graph with all of the dots plotted on the graph. And the idea is to get the line to fit the best so that when you subtract, take the number on the line and subtract it from the number, it's as close to 0 as possible. It's the same concept. Okay.
So you want two things, you want less error, small error, plus you want your comparison to be equal to show that the model's a good fit.
Right, the less error you have though, the more it will be equal,
Okay.
right? Lower residuals means less errors, means your model fits. Those all things link. Sorry, I just want to look at where it is on your output.
Which one?
For your,
Structures.
oh, thank you. Okay, so when you do your output, you'll have the structure matrix and then the pattern matrix. On last week's stuff, it was the first two full pages. So we're going to go over those two outputs. So in pattern matrix, it's giving you basically standardized values. It's like a beta.
Where's that on here?
Are you looking at last week's?
It's not on the list, it's this one.
Oh, it's under oblique. And then on the structure matrix,
What page?
the first two from last week's.
It's actually, it says 6 and
Oh.
7 on the back, or it's the first page, depending on how you hold it.
Oh,
It's this packet.
Oh, I guess that's,
Yeah, but they're all in the line anyway. Because this says 1 of 4, and then it starts over again. He smushed two different things together.
You see the first page of the thing? Yeah, that's it.
So then we're looking at the very back page.
There's nothing to it.
now flip it over onto the back with the one you have, Christina. It should say at the
It
top.
says CF, AEX on the front page.
It should say at the top pattern matrix or structure matrix, and then the next page it says pattern matrix. We're going over what those two boxes are. In structure matrix, it shows how much variables correlate under the factor,
So, right?
how much variables correlate with under the factor that they're listed. And so what you really want to remember is that pattern matrix it's the standard. They're like beta weights.
You said there's still large data weights?
Yeah, they're standardized. Okay.
Should I go back to
We're just going next line.
put on the
So these two matrices, what are they giving this information on?
On loading, correlations for each. It's just loadings under the oblique,
So these are rotated.
but it's oblique rotations. Just the two types. That's free plot with the bubble and
Hold on, so the pattern matrix is your oblique?
yes,
And so is the
As
structure
well as the
matrix.
structure matrix.
yeah.
I'm with the pattern matrix.
It's the one with the beta weights.
The structure
You
matrix?
said the structure matrix was beta.
No.
No, it's pattern matrix was beta weights.
Come on, guys. Such easy material. Just
What
kidding.
is the difference between the structure matrix and the pattern?
Pattern matrix gives you beta weights, the standardized. Structure matrix doesn't. They're unstandardized.
Just depends on what you want to use it for.
Aren't beta weights standardized?
Yeah,
I
that's
said
that's
pattern
why.
was like beta weights.
So shouldn't the structure matrix be the one that's saying that?
Are we confused?
Why?
Are we now taking issue with how they're named?
Yeah.
That's outside of my territory.
Yeah, I don't get
I did not go into the creation of SPSS.
So just to clarify, because I wrote it down backwards, the pattern matrix is how much variables correlate under the factors listed and are standardized.
That's everything you said up to our standardized was the definition for the structure matrix.
Pattern matrix.
But they're very similar. It's the same idea. It's just for the pattern matrix, then you're talking about standardized weights of the variables.
Okay, so the pattern matrix is the standardized weights of the variables, and then the structure matrix is how much variables correlate under the factors that
But they're unstandardized.
are. Okay.
Forgive me, just to clarify, the structure matrix and the pattern matrix both demonstrate how much the variables correlate under the fact that they're listed, but they're just the two different ways of describing it, standardized versus unstandardized.
Right, and they could fall under oblique rotation as
Right.
opposed to orthogonal, which looks at the rotated component matrix.
Sure.
That's not variables, it's factors. We get rid of the word variables.
Thank you,
Right.
thank you.
If you can. It doesn't actually ever happen. Okay. So communalities. Okay, this looks at the amount of variance a factor accounts for in the variable.
Amount of variance.
The amount of variance a factor accounts for in the variable. So think of variable as like a bigger term, and these factors are the pieces that make up the variable. You can picture that in your head.
Is commonality on our concept list?
Yes.
under oblique rotation. We'll go back to the ones in the middle we skipped. Don't
We're
worry.
still back, we're still in oblique.
So for
Nope, now we're on commonalities.
The commonality is part of oblique.
No.
I said it's under oblique, like directly after oblique on the list.
Okay.
Gotcha.
For the example we did today, would be like personality, be the variable, and then like type A and the other ones are the factors, something like that. Is that what you're talking about?
Well, I would think, I don't want to confuse you.
No, because it'd be like,
Can you give an
You could say like type A is a variable, and then what constitutes someone who's type A? Like what adjectives would you use?
Certain.
Right, those would be your factors that
So the
load.
communalities would be using that, I just want an example.
So communality, so you're looking at the variance that the factor accounts for in the variable. So like how much does anal account for in type A? Is that right? Okay. So you're looking at the relationship of the variables of that factor. So when you have high values, you have high loadings. So-
High values, you have what?
High values for the communalities gives you high loadings. So when you want stuff to cluster together, you want high communalities. Okay, so on the opposite side of that, a low value means that there's a lot of unique variance, which means that you have low shared variance. And what that tells you is that these items aren't loading onto any of the the factors or the variables. Where do you find it?
Can you repeat that last part, the low value?
Yeah, so low values mean that you have a lot of unique variance, which means that you don't have a lot of shared variance. They're just opposites. And then it's bad because then that means that the items aren't loading onto any of the factors. So you don't really know what's constituting what. And in that same packet from last week, the back of the first page, there is a table just labeled communalities. And if you look at the extraction value, he actually went through and he pointed out, I'm assuming it's analytical. It's like halfway down the first column. It says 0.397, and he said that's a low communality.
Where is this at?
It's called page 2. Called page 2. It is page 2. It's the back of the front page. It's in the communalities table. It's under, you look under extraction. And he just happened to point, Dr. Gevirtz happened to point out that like analytical had a low communality. So that means that that's not loading on that particular factor.
And what is the thing called? There's like several page 2s.
Communalities. It's the back of the first page that said CF, AEX. That would be the front.
Means analytical is not loading on what factor?
I don't know what it was.
Is there a way to tell from that? No.
No, because you were doing, it said you were doing principal component analysis, so there is no model. So you're just sort of playing around with it. Does that make sense? And I knew it was principal component because it says it at the bottom of the communalities table.
We have less than 5 minutes to wrap up.
So when you,
Why?
Because if another class comes in.
No, we have this one till 1 o'clock.
Oh, right.
I hope. That's what I reserved it for.
Okay.
Maybe they're just aiming.
So at the bottom of the table, it labels it.
Yeah, just, it says extraction method, principal component analysis. Okay, we good?
like, so each of those values is relating to how much or how high it relates to all of the other factors?
No, how it relates to the variable. To the main variable.
But these are all
We haven't labeled it yet. We don't know what the main one is.
the main variables.
Yeah, like in this case, it's principal component analysis, so you're not sure what it is yet. Do you know what I'm saying?
So it's relating, it's how much this is related to.
Yeah, because this will tell you.
Thing we don't know.
Yeah, because you don't know what it is because you don't know what it's made up of yet. When you can figure out the pieces, right?
Okay.
Then
And
you
we
can
start-
label it,
Okay.
right? Sort of like what we did last week.
But this is like, if we looked at that screen graph over there, it's taking in everything and we want to cut stuff out.
Yeah. Okay. So number of factors to retain. So you look at, let's see, I've got written Kaiser rule, which refers to the eigenvalues.
Kaiser rule, what?
Kaiser rule refers to eigenvalues. Do you remember learning that? Eigen, E-I-G-E, oh, Kaiser.
Kaiser roll? Like the
Rule.
roll?
Let's see, you can also look at the percent of variance accounted for. I like to look at the scree plot because I'm visual, that's easy for me. And the scree plot is just a pictorial representation of eigenvalues. And lastly, it also could depend on, what your hypothesis was. So if it was theory-based, it may depend on what your theory is, or what you're expecting.
Can you give us an example?
I think it's just, what you think might happen. Deciding how many factors to retain. They want an example for like the theoretical. I mean, that's just, you decide basically. Because it's your theory, right? You've proposed this theory, you've created this hypothesis. Do you know what I'm saying? And then you decide.
That the factors are going to load in a certain way?
No, how many factors to keep out of this whole process.
So you can choose if you only want 3, or if you want 5, or... if you're a good statistician, you're going to look at the scree plot and you're going to say, okay, well, really, there are only 3 or 4. You're not going to say, well, my theory wanted 6. You have to go with what the evidence is.
You talk about eigenvalues and eigenvectors.
Yeah, we should do that. Yeah, so the eigenvalues, okay, these are the sum of the squared factor loadings for that particular factor component. Again, it's the sum of the squared factor loadings for that particular factor component. Okay, and you can also think of it as the percent of variance accounted for by that component, or that factor. So the eigenvalues, you add them all up, and then it gives you the total amount of variance captured by the model. Which one?
You can do it both ways. You can add up, square and add down. So for this one, eigenvalues, it's still square and add.
For which case?
You can do it in under the factor itself.
Oh, here we go. Okay, so for eigenvalues, you square the values, and then you add down. Do you guys remember looking at the component matrix? This was from last week. So squaring and adding down the columns gives you eigenvalues.
Which is obviously then going to get you the amount of variance captured by that particular factor. Now, if you square and add across, it equals your communalities for that particular item.
And that's in the structure.
That's in your component matrix.
Component.
Yeah, that's the one with all of them, basically. It tells you how many potential factors there are and how they related. So if you square, so obviously on this one, factor 1 had the most loadings. So you square and add down, that gives you the eigenvalues. It's basically, you square each number and then add them all down, and it gives you the amount of variance captured by that particular item. If you square and then add across, it's going to give you the communalities, which is, how much each particular item itself, like leadership ability, how much did it contribute to the model overall, right?
So I said, in my notes at least, looking at Kaiser criteria. Do you know that? Is it important?
What about it?
Just that the total value is greater than 1. So this again is referring to Kaiser. I think we just talked about this, right? So you want a greater than 1.
Classes and vectors. eigenvectors. With eigenvectors, it's basically a line of best fit. So after rotation, the vectors are rearranged to optimally go through the cluster of variance.
Repeat that? After rotation?
The vectors are rearranged to optimally go through the cluster of variance.
After the rotation, the vectors are rearranged.
To optimally go through the cluster of variance. So eigenvectors are related to eigenvalues. It's again, it's looking at where things are loading.
And the difference?
One's a line of best fit, the other looks at variance.
The vector is a line of best fit, the eigenvector.
He has percent of variance on your thing. Again, it's just another way to determine how many factors to keep.
I'm not seeing that on here.
It's in the middle under eigenvectors.
Oh, okay.
It's
Deciding which factors to keep.
based on, the total amount of variance that they explain.
So you want the highest ones
Well, so in this one, you would be looking at, so in the total explained variance on this page, it's the one that looks like that. So if you were going based on percent of variance that it accounts for, you look at factor 1 accounts for 17% of the variance, right? And then as you go in, you've added factor 2, it accounts for now, those two factors together account for 28% of the variance. Factor 3 added in accounts for 33% of the variance, right? But then as you add in factor 4, it only accounts for roughly 5% more of the variance. So the more factors that you add in, obviously the more participants you need, the less that variance there's going to be spread. So sometimes it's better to have less factors, especially if the addition of each new factor isn't explaining the model any better. It's better to stick with maybe 3 factors than moving to 4, because the 4th factor will explain your model, unless it's based off your theory, right? Unless your theory says otherwise, or unless you hypothesized otherwise, then you have plausible reason to keep that 4th factor, but the math is showing you that it's not really contributing, so you have reason to get rid of it potentially, okay? There's just different ways of looking at the data and deciding what you want to keep and what you want to get rid of.
Just the plot.
Yeah. Another way to determine how many factors you want to keep is looking at the scree plot. You want to get rid of the factors when it starts to get the rubble on the hill. Remember he had the mountain and all the rubble? So it's where the plot starts to even off. That's when you want to start getting rid of those factors.
Okay, remember those are just your eigenvalues
Right.
on a graph. Okay, so factor scores. This is when you have one factor and it's used as a predictor to create your factor score. So you find one factor and you can use it as a predictor. It indicates the strength of that factor for the individual in standardized form. Okay, another way of saying that is you have the standardized version of the loading times the actual raw score.
Standardized what of the loading?
Standardized version of the loading times the raw score, or the actual score. And then if you're using SPSS, which you would be, it's just saved as a new variable. Okay, so it's, I think they call it like a predictor if you're using SPSS. Okay, and then the last thing, the significance of loading. So you're looking at each factor's items and see where it loads. So basically, again, how much each item contributes to that factor. Do you know where in SPSS you should look? The rotated component matrix. So he asks you, I think we went over this, to look at loadings that are greater than or equal to 0.4. And then you can have those clustering together to give you a particular factor.
Did you say that last part one more time?
Yep, so you want to look at the loadings that are greater than or equal to 0.4. Okay, and then that's your cluster, right? And that's how you're going to decide how to name your new factor. Do you have these values? All right, so just quickly to give you a better idea, so 0.7, okay, that's considered excellent, so that's a really good loading. 0.63 is very good. 0.55 is good. 0.45 is fair. And 0.32 is minimal. Okay, so if you can see if you're looking at greater than or equal to 0.4, you're taking some that may not be like the most correlated, but it still warrants inclusion and, you know, naming what your variable might be. Does that make sense? Okay.
So anything with fair you want to address? Fair
Yeah,
enough.
fair enough. Okay, because those are your common elements that you're using to create a new factor. Okay. We good with this page? Make sure you really know the difference between confirmatory factor analysis and then exploratory. But then under exploratory, you know, principal component and factor analysis. So don't confuse CFA with FA. Okay? Different things. One is theory, one is theory, or one is theory, one has a little.
You said, but under exploratory.
Remember, we had the two parts, principal component analysis and factor analysis. Okay, so don't confuse those, because on the test, he might say factor analysis, don't think it's confirmatory factor analysis.
Okay.
Okay? So, if you're confused, ask him, because he'll probably tell you which one he's talking about. Okay? So look at the back of your notes from today for the structural equation modeling. I don't know if I have anything for this. Do you? Yeah.
I want to see if I have anything for my exam 3 or 4 review.
obviously something we need in space.
I have like very minimal. I must have put somewhere else though because I wouldn't have. Okay.
So let's go to mediators and moderators quickly. Mediation. Didn't we go over this last time?
Or the time before
We
too.
went over it, but there was like a question or two that he said were very easy that like most of us got wrong.
He always says that with every question that everybody gets wrong.
Oh, right, this is where we
Easy.
drew the picture.
Everyone got the
Yeah.
exact opposite. So it wasn't just wrong, it was the exact flip.
So what was the question? Do you guys remember?
One was an mediation, like they want to
Oh.
reach it, yeah.
Okay.
Did I tell you the wrong thing in review?
I mean, I remember the definition, I don't think I mixed that up, I think just the question didn't convey that
Okay.
definition.
Okay, so it's just a hard question.
All right.
Okay, I just want to make sure I wasn't telling you because they are
Huh?
sort of similar.
So then what is mediation?
It expresses some sort of causal link, there's another factor that is causing that interaction or correlation between the two.
Yeah. So it's looking to explain a relationship.
Yeah.
Right. So then the moderator then is? Yeah, it changes or alters a relationship, but does not explain it.
So mediation explains, that's what highlights that?
Yes.
Mediation, you want to use the word causal.
Yeah.
That's the important part.
And then so mediation is tested through, right?
The Sobel preacher test.
And then to test them, it's used Sobel preacher test of mediation. For a moderator, what are you using to test it?
It's really easy.
It's you're using the interaction in ANOVA, right? Moderation.
Think of it as like a buffer. Okay, so it changes the relationship between your two variables. Okay, but it's not a cause. Right.
It just adds noise and error.
Yeah, so these the example
what?
the example I have in my notes is like, okay, you have this person, right? And then they have a particular shoe size, okay? And then a moderator would be being pregnant because women's feet swell or whatever, and their shoe size might go up. Okay?
Be a moderator, pregnancy.
It's a moderator because it doesn't cause, a lot of other things could cause that, like maybe there's overeating and they're getting fat or whatever, I don't know. But they're, whatever, sorry.
It's a great example.
Sorry for moms. But do you know what I'm saying? So it's not the exact cause, but it does somehow change that relationship. Doesn't explain away all of it, but it changes it somehow.
So another example would be
Why, you can't relate to that one?
quantity of food intake, the size of the individual is related to quantity of food intake.
Right.
And maybe exercise would be a moderator.
Right.
Mm-hmm.
Or you can say studying well on the exam, or studying well and class attendance is going to predict exam scores. But if you drink at night before the exam, it's going to change that relationship, right?
You do a lot better than what it is.
Did I get that
I totally did it now.
It's a lot easier.
So, and then for a mediation, A and C have a relationship because of B,
Yeah.
right?
So the example you just gave with the example score is moderation.
Mm-hmm.
Right. The pregnancy one's hilarious. Okay. We're gonna get on all type 1 and type 2 bit. Toilet baby. Next, man. Okay. Okay, so let's go over the components of the path diagram for structural equation modeling. So you have the endogenous variables, which are,
The arrows are going,
to it.
yeah, in.
Right.
And again, I loved how you knew how to ask in a way that didn't embarrass anybody.
Oh,
Thanks.
yeah.
I'm glad you guys brought that up. I wasn't really paying attention.
Endogenous variables also get errors or disturbances. So exogenous variables are variables with arrows going away from it. Makes sense.
And exogenous variables can have arrows going into it as well.
Correct.
Yes.
Right. So only endogenous variables are the ones with only variables going to it. Because you're going to have some exogenous variables that have both, right? They have arrows going to it and then arrows going away from it. Endogenous, we identify them because they only have variables going to it. So they're usually the ones in the far out right-hand corner of your path.
So exogenous can have arrows going in too, but endogenous cannot.
Correct.
Okay, so this isn't,
That's a covariate.
right, so this is considered linear if it's covariate.
And yeah, it's that loop. No, those loop. And so the covariates are the ones with double arrows.
Now, say you have a model where you have a covariate between two variables. Though, other than that though, those variables are exogenous. Is that's still considered an exogenous, or would it be like an exogenous like covariate, or like how do you?
They are both. So they're exogenous and they're covariates. However, when you're doing your path part of the equation, you don't double count the covariate part of it. Does that make sense?
Sort of.
So when you go into, he has the equation, I think.
Oh, you're talking about you put in just the R value instead of the beta value twice or something.
Right, you just want to make sure you're not counting it twice, right? So,
Right.
You don't multiply through covariance, but
right. Right.
Right.
Yes. Yeah. So, and then we said disturbances or errors go with endogenous variables. You want to look at beta weights for one-sided arrows. So both endogenous and exogenous variables you get beta weights for. For covariates or the double-sided arrow, you can look at the Pearson correlation table for those values. And then obviously single arrows indicate a causal relationship.
Can you go over all of those again?
Yeah, of course. So for one-sided arrows, you add in beta weights
So that's endogenous.
and exogenous. So anytime you have just a single arrow, it's a beta weight. And remember, you're running a regression for each of these. So, you know, if you say you have, right, but when you're looking at the number, you want to make sure, so if your model says you have food intake, exercise, weight loss, if that's your path, to get the arrows from food intake to exercise, you want to make sure that food intake is your predictor and exercise is your outcome, and then go into exercise as the predictor, and then looking at weight loss as the outcome for that path, right? For the beta weights. Is that making sense? If it's not, I can show you what I'm talking about. But you just want to make sure when you're trying to get the particular beta weight that you have the right predictor going to the right outcome, because, I mean, you're going to have to run multiple regressions to get a big model, obviously. Okay. And then two-sided arrows, Pearson correlation table. Sorry, I kind of sidetracked there, Heather. And then the single arrow indicates a causal relationship.
So your covariates, you wouldn't say that those are causal, right? That's just showing an association.
Single arrow is,
Causal?
oh, there was some table or something.
No, two-sided arrows
Correlation.
are the Pearson correlation table. That's where you get those numbers.
Where did the semi versions?
I don't have that written down either.
Yeah.
Did he go over semi-partials and path coefficients today really quickly? Did he say anything about them? He just mentioned the betas?
It was from last exam, the partial. we didn't mention it.
Talk about that, like standardized
No, when he was going over the structural equation model concepts at the end of class today, I wonder if he touched on that one in relation to path coefficients.
No, we haven't talked about that since we've been discussing path coefficients and models.
Yeah, because I don't understand where that you would use the semi-partials for the path coefficient. I've only heard, he's only talked about using unstandardized, standardized, and Pearson correlations.
Yeah.
For the, when you were talking about the single arrows and getting the beta weights and putting them in, we get those from which table?
Where is your regression output? You're looking at your coefficients. So it's under the ANOVA. And you want to look at whatever the predictor is, and then look at the very bottom, right underneath that table, to see what is listed as the outcome.
It's not in the packet.
Okay.
Yeah, on that particular.
So it's, say one more time.
So you want to look in the coefficients for the, under that coefficients table, and then you want to look at what is the predictor's name, and then see what it's referring to and relate, like what outcome it's referring to, and the outcome will be written under each model, or each coefficient table itself.
And this is for what?
This is for the exam when you're looking at the output. You've seen
It's
it.
just a normal.
Yeah, it's this the normal one. But he'll give you multiple regression outputs. That's how you'll be able to tell which one's referring to which. So you want your parameters to be less than your observations. I'm gonna write that down.
What?
Yeah.
Go ahead.
What is this falling under?
This is falling under path diagram in general. Trying to think what it relates to.
We want predictors to,
You want parameters to be less than observations. And he went over it in principles of identification. And that second page of your output is all three of what we're going over next, just all slides. But so basically parameters, the equation is paths plus covariates plus exogenous variables plus disturbances. That those equal the number of parameters you'll have. And then to determine how many observations you have, it's K, which is number of variables including the outcome. So number of predictors.
The predictors?
No. So observations equal K. And K is so K times K plus 1 divided by 2 equals observations.
K times K plus 1.
That's your equation for observations.
And K is the
And-
number of predictors you have.
It's the number of variables, including your outcomes. So it's the number of predictors and outcomes in your model. And so he goes through the equation in that center slide for observations. It's really, really teeny tiny at the bottom of that slide. With reproduced correlations, it's checking how well the model fits. You compare the computed value to the Pearson correlation table. Computed value. And you need it to be within 0.05. Yeah.
So with reproduced.
Correlations, it checks how well the model fits. Okay.
Are they waiting for this classroom?
Yeah.
Okay. And it compares the computed value to the Pearson correlation table.
No, she said she had to cancel it, and she wants me to tell you that she needs to reschedule yours too.
Are you kidding?
She has an emergency patient situation.
Oh, good, I'll have to do it, okay.
You want it to be within 0.05.
Thank you.
Under? 105?
Yeah, 0.05 or less than. That's, your difference score, basically. So a direct path is when you have an arrow going from one straight to another. An indirect path is when you have to move through variables. We're almost done.
Oh, okay.
You guys need to come in here?
We have a class at 1.
Okay, yeah, we're done.
And indirect is?
Indirect is when you have to go through a variable to get the full path. So in this center page, you can take path 5 to get from exercise to illness, or you can go from path 9 to 1 to get to it, right? One's a direct, one's an indirect, sorry.